Hello everyone and welcome to another Motec webinar. My name is Pete Swinney and today's subject is helpful hints on boost control plumbing. This webinar is going to be about getting the boost control system to work correctly via the plumbing of the turbocharger system itself. Boost control or closed loop boost control in an ECU is dramatically affected by how the control system is set up. The plumbing of the hoses for the control valve, the turbocharger itself, everything affects how the ECU responds or how the system will respond to inputs from the ECU. So today we're going to talk about a few different boost control types. Restrictors, some of the control valve differences, some precautions when we're getting this thing set up, some ECU precautions that we're going to go through, things to check inside the ECU, and perhaps a way of testing maximum boost pressure. Alright, so moving along. There's actually a multitude of different ways you can do to set up a boost control system, but kind of the 5 ways that I've identified are here in front of you. So we can have a no control system whereby the turbo, in fact you can have a dead no control system with no wastegate at all, and some diesels have that. But most systems today have some sort of wastegate that gets rid of exhaust pressure to slow down the turbocharger wheel. Now a very simple system, which was out about 20 years ago perhaps, where you have an integral wastegate, and a simple spring operates against the poppet valve, and once the pressure from the turbocharger exceeds the spring pressure, the gate opens and the exhaust pressure is relieved and the boost is limited to basically that spring pressure. So there's no control of that other than the manufacturer setting the tension of the spring. From that system we went on to a manual bleed system, which you'll see shortly, whereby we waste air away from the pressure on the wastegate diaphragm and therefore not let it achieve the boost required to lift the diaphragm against the spring. That way the turbo can make, say, 10 pound of pressure before enough of that pressure gets to lift a 7 pound spring. So the more you bleed away from the system, the higher the boost. Then went to solenoids, where instead of a manual tap, a solenoid bled air away. Then a 3-way solenoid did it a little bit smarter, and then we went to a remote wastegate on large turbochargers, and race vehicles today often have a remote wastegate and a 3-way solenoid. So we can have a look at each system. So here we can see the system. Let's turn the arrow on. Basic no control system, where we have the compressor from the turbocharger, the boost line going to a diaphragm or a chamber above the spring. Now the spring is overcome by the boost pressure on the positive side here of the diaphragm. So as the pressure goes up in the turbo, it also goes up on this side of the diaphragm, and then once the pressure here exceeds the spring pressure, the wastegate actuator moves down in this case and opens the wastegate. So moving on from that system, we then had the manual tap system. So in this case, the compressor here runs the pressure to the actuator as per last time. Now if we go with the example of a 7 pound spring here, the 7 pound spring requires 7 pound to lift the gate. Now if we waste out of here 3 pound, then the turbo's got to get to 10 pound before there's enough, the 7 pound here, to lift the spring. So effectively, by wasting air out of the line and out to atmosphere, stop the pressure getting to the diaphragm on the wastegate. So customers in those days with this kind of manual valve, and when I say manual tap, that's like a tap that controls the water on your house sink or your house taps, and basically you just start scrolling this tap out and bleed more and more air away. Now the problem with that system is that you have to sometimes get rid of lots of air out of here to stop enough pressure getting to here to allow the boost to go high enough. And of course, if you want different boost levels for different times, it's very difficult winding on and off with the tap. Obviously you should be driving. So not an ideal ongoing dimensional way of controlling boost. Now, modern vehicles from perhaps 1995 on started going to a solenoid that took the place of that manual tap. Now this solenoid is a pulse width modulated solenoid, and when it's turned on and off, bleeds air out to the atmosphere. Now that solenoid is controlled by the ECU, and with the Motec ECU we wire it up to an auxiliary output, and that auxiliary output pulses the solenoid to control the amount of air that is being wasted away from the system here. Now those solenoids will only bleed a certain amount of air away. As you increase the duty cycle on the solenoid, the airflow increases. But what we find on factory cars today, such as the Evo and Subaru, is that the solenoid will only raise the boost by a certain amount. So for instance, if we have our 7-pound spring here, and if we maybe turn the solenoid on at 100% duty, in other words open it right up, we might only be able to get rid of an extra 7 pound of air out of the waste side. So that would mean we could get a total of 14 pound boost extra in the turbocharger. So to help that effect, and to allow us to lift the boost even further, manufacturers put a restrictor in the line. And what that means is that the solenoid doesn't have to pass as much air out of the system to get a boost reduction here on the diaphragm. Now the problem with this is that the restrictor itself forms an airflow restriction, and therefore a response, the response time suffers. Now if you come across, for instance, an Evolution 7 or something like that with a solenoid on it, and you want to lift the boost to, let's say, 22 psi, you'll find that with the setup as it is now, the valve, even at 100% duty, will not lift the boost high enough. So you have two options. Option one is to increase the spring pressure in the diaphragm here. So in this case, if we bring the spring pressure from, say, 10 pound up to 14 pound, that means we'll get an extra 4 pound of boost range using the solenoid. Sometimes that's difficult to do, to change the spring, and sometimes it's not legal to do for Group N rally rules, for instance. So one of the things that you can consider is changing the size of the restrictor inside the line here. And by doing this, you can take the restrictor from, say, a 1.1 millimeter hole down to 0.7 of a millimeter, and that will allow the solenoid to pass more air out. Well, the solenoid won't pass more air, but it'll allow, because there's less air flowing through the restrictor, the solenoid can get rid of more boost out of the line proportionally. So if there's less pressure flowing through here, or less flow, the solenoid doesn't have to flow as much out to get the same reduction. And this way we can bring the solenoid into a range that is programmable. The aim of this whole webinar is to get a system in place whereby the ECU controls the duty to a solenoid, and the duty will see a boost response. So if we have a 10-pound spring in here and we want to run to 24-pound boost, and the solenoid at 100% duty doesn't give us what we want, well, then no amount of computer tuning is going to give you the result you want. So you need to get the system to respond to the ECU's control. In other words, a duty cycle being pulsed on the valve between 0 and 100 gives you a boost change that you want. Okay, so that's the aim. So example 1 was we could scenario 1 was we could lift the pressure of the spring. So if our boost range, for instance, for our particular type of racing may want to vary for this customer between 18 and 24 pound. So in that scenario, you should aim in an ideal world to have an 18-pound spring. So the minimum boost will be when the solenoid is off and the spring is 18 pound, so you should get 18-pound boost. And to raise the boost from 18 to 22, the solenoid will simply start pulsing air out of the system and waste that air away so that less boost effectively gets to the diaphragm and therefore the spring doesn't lift. So this way you have good control between 18 and 24 pound. Right, so you need to set up the mechanical part of the boost control to do that. So that's our simple system that arrives on, as I say, more modern turbocharged cars. They run a two-wave solenoid bleeding out to atmosphere. And as I say, also the majority need to run a restrictor because the type of valve used doesn't flow a lot of air out. Of course, you could say, why don't we just put a bigger solenoid on and flow more air? Well, two reasons for that. One is you can do that, but obviously the more air we're wasting out, the more boost we're actually wasting as well. So effectively we've got a boost leak when we're using this thing. So we want to try and have the thing not flow a lot of air out, not waste a lot of boost, but still control. And the other thing is that a lot of larger flow valves don't have a very good linear response to the duty cycle. So what that means is if we lift the duty cycle on the valve by 10%, we want a kind of a set response of boost change for 10%. We don't want a solenoid that has a 4-pound boost increment for 10% duty change, and then at another point on its, say between 20 and 30, it lifts at 4 pound. Between 30 and 40, it lifts at 10 pound. Between 50 and 60, it lifts it out of sight. So we want a nice linear range, and that way the ECU, when it goes to PID closed loop control, has a better chance of predicting the correct amount of duty to achieve the correct boost. Okay. So moving on. Now, another valve that is available doesn't increase flow, but you can purchase from anywhere, obviously Motec, is a 3-way solenoid. Now this is a different type of solenoid, and what this does is it doesn't work bleeding the boost away from the turbocharger. It's actually got a clever port design where when the valve is off, the solenoid acts as if it was a straight piece of pipe. So when the solenoid is off, that boost, in the case with an integral wastegate, goes down, is maintained to spring pressure. So you can see by the thick blue line here in the diagram, the valve is off, the boost goes straight through, and the boost is limited by the spring pressure itself. When the valve turns on, it blocks off this port, the port between the turbocharger and the valve, and opens the port between the wastegate diaphragm area and atmosphere. So what that does is physically let the pressure out of the diaphragm and causes the wastegate to close if it were open. And so when the valve is on, then the boost goes up. Now this is actually the opposite to why a two-way solenoid valve works. So just pop back, we can see that when the valve is on a two-way solenoid, it leaks air away and the boost pressure goes up because pressure does not make it to the diaphragm to open the spring. But with a three-way solenoid plumbed in this fashion here, the three-way solenoid, when the valve is on down here, then no boost gets to the diaphragm and therefore the wastegate stays closed. Now, an important thing to remember here, and this is to do with speccing your actual wastegate diaphragms and springs, is that if you take a spring, let's say of 10-pound spring, and you want to operate the system at, let's say, 28 pound, in this example here, even though we haven't got any pressure on this side of the diaphragm, the spring itself should keep the wastegate closed. What happens is that the back pressure from the exhaust manifold push up against the spring, opening the wastegate. So if you're going to be running 30 pound of boost, then again this all comes back to speccing the system on the minimum and maximum boost required. So if your minimum boost requirement is going to be 6 pound and your maximum boost requirement is going to be 30 pound, and using this type of system, you've got some problems. You're actually going to need to do some clever work with multiple solenoids to keep the wastegate closed for higher boost levels, yet be able to open it lower. But most of the time, for most applications, I would suggest that anyone who's running 30 pound boost usually doesn't require a lot less than 20. So if that's the case, you should spec the spring in your wastegate actuator to be 20 pound, and then when the valve is on, in this case, we can achieve 20 pound boost, and 20 pound spring, if you like, has plenty of tension against the wastegate poppet valve to keep it closed against back pressure. Still won't be always the case, and as you go up in wastegate poppet valve diameter, then heavier springs sometimes are required, or actual pressure valves to push pressure onto the diaphragm when you need it to stay closed. Up on the underside of the diaphragm to stay closed. And the remote wastegate has features to help this. So just to recap on this is all difficult to get your head around if you're new to it. So with a three-way solenoid plumbed up as per the way Motec tells you to plumb it up if you buy their solenoid, has the boost going down when the valve is off and boost going up, valve is on. Okay. What this actually means with this valve is a couple of key things. One, you don't waste any boost by doing a bleed system. There is no waste of pressure out of this side of the compressor. So you're not wasting anything out to atmosphere. A very small amount exits out of the wastegate itself, but it's insignificant. So the computer actually pulses halfway between these scenarios in real life. So it pulses on and off constantly between the two to effectively do a bleed style system. So you do waste a small amount, I must correct myself. Alright, so the last system that we're going to look at is using an external or a remote gate, remote wastegate. And the more higher performance systems you'll see where you have larger aftermarket turbochargers that don't have integral wastegates fitted, use a remote gate. And a remote wastegate does have some advantages, namely a second port. So the remote wastegate is quite a bit different. The spring is on a different side, so it works a little differently again. So the two examples we see here are for the valve going on and the valve going off. And you can actually plumb this a number of different ways, but again, this is the way that the Motec, I think it's V14 drawing, says you should plumb it, and the way we'll talk about it today. So in this case, when the solenoid, when the valve is off, pressure goes from the turbocharger to this side of the spring, and pressure also goes to the bottom side of the diaphragm, and effectively the two neutralize, and the wastegate doesn't go anywhere. When the valve is on, the boost is wasted out of this part of the spring or of the diaphragm, yet it's still got boost on the underside of the diaphragm. So what this does is the boost underneath pushes against the spring and wastes that small part of air out to atmosphere and opens the gate. Now what it does is it does this very quickly because the boost is coming through, and again on the diagram V14 you'll see that we recommend a larger diameter hose to go to this port. So a larger diameter hose obviously means we're speccing it like that to get the flow to this point as high as possible. And what that means is that the response to the opening of the valve, the response to the actual movement of the poppet valve here is very fast, and the poppet valve moves up very quickly as the port here is opened. So as the port is opened, the air from this side of the diaphragm wastes out, and the boost on the underside of the diaphragm very quickly lifts the valve off its seat and allows the exhaust to be bypassed. So when the valve opens, of course, the boost goes down. The wastegate opens, the boost goes down. So in this example, as in the other one, the computer pulses between off and on to vary the control on the wastegate itself. And this is a way of getting very quick boost response. Often when customers, drag racing customers, etc., go for high acceleration rates from a low RPM where there's no boost made, boost comes on very quickly, and you need the system to be able to get rid of boost very quickly, otherwise an overboost situation can occur. So the quicker the boost system will respond, or the mechanical aspect, the plumbing, and the mechanical side of the boost relief can operate, then the quicker that an overboost situation can be avoided. So again, the computer can only do so much. It's all about the plumbing and the way the boost control system is designed as to how well it responds to the computer's request. So, assuming you get the plumbing correct, but before you actually go to test that it's working correctly, I'd like you to make a couple of adjustments in the ECU for some safety. Because if you get this wrong and you've got maybe a test driver or rider who's a little unsympathetic, not necessarily going to go out there and respect the engine, and it could easily overboost and cause damage. Now there's a couple of things that we need to be aware of. In the case of overboost situations, there can be some unusual incidents if you don't have some things sorted. So in a manifold pressure setup, so under our input setup in the ECU manager, and in the manifold pressure part of that, we have actually a default value for the sensor if it goes into error. Now, if you happen to be running, as a lot of our customers do, a Delco 3-bar map sensor, that's a sensor that reads 2-bar positive. So that means effectively it will measure up to approximately 28 pound of boost. Now, if there's a chance that you will exceed that in your boost control tuning, then the potential is that the manifold pressure sensor itself will go into error from the overboost situation. Now, when it goes into error, the ECU, like all of our sensors, the ECU substitutes a default value. Now, if you don't put a number in here, our default number for our manifold pressure sensor is 100 kPa. So what that means is if you overboost past this sensor's limitations and it goes into error, the ECU will substitute, go on the default, a value of 100 kPa. Now that's effectively leaning the engine out in a rather large way, and we don't want to have that happen. So in the case where you are running a 3-bar map sensor, then I would suggest that you put in a substitute value of 300 kPa, and you may even choose to make that 350 kPa. Alright, so just to recap, if you are running a 3-bar map sensor and it's possible that you will boost more than 2 bar of boost, then you should put in a sensible default value for the computer to use. Now the other thing that's useful to do, and this is along with engine temp and air temps, is to configure the warning alarm for a high boost application. Now again, let's assume that our boost level for this test might be 260 kPa. We never want the boost to go over 260 kPa, which is 1.6 bar of boost or 160 kPa of boost. So in this case, especially if we're tuning with the laptop on the engine dyno or in the car, then we can have an alarm flash up in front of us to let us know that there's been an overboost situation, so we can get our foot off the pedal, shut things down. So by ticking the box here and typing in the sensible number that you want the alarm to go off at. Now you can actually also configure a warning light up to go off at the same point. So any of these alarm levels will trigger a warning alarm if you've got that configured on our auxiliary output. So a driver could be instructed to get his foot out of it if the red light goes. The reality, unfortunately, with setting up boost control is that you have to test, and if you don't have a dyno, then you've got to go out in the real world and test. And the overboost scenario is very common while you're getting this right. And in fact, we really do need to find out what the limitations of the system are in order to be able to control them with the computer. So these are 2 precautions that you should look at doing. Another precaution that you can actually have the computer shut the fuel off when you get to an overboost situation. So in the boost control setup, so functions boost control, you'll see a parameter here called Overboost Cut. And if the ECU detects any more than, in this example, 250 kPa, so in other words 1.5 bar boost, it will do full fuel cut. And if you are riding a motorcycle or a jet ski or even a car without a seat belt and this thing goes into full boost cut, you'll hit your head on the dash. It absolutely cuts the power, and from holding against the G of acceleration, all of a sudden there's none, so be careful. It will cut the fuel at 100% until the boost drops back down below 250. It's not very good for drivetrains and things like that, but it will protect the engine, so use that with care. The other thing that we need to set up while we're in this part of the control is the type of boost control that the computer is going to do. Now there are 2 distinct types of control that our ECUs can use. You can have a duty control, and what this means is that you type into the boost aim table the duty that you want the solenoid to use. It's not a boost level, it's not a closed loop control, it is simply at this, for example, RPM, I might want to use 40% duty. And when we're setting up the boost control system, we will conduct testing at specific duties. So the duty means the amount of on time versus off time that the solenoid operates with. The longer the solenoid is on, will alter the boost, and depending on the solenoid itself, on time can make the boost go up, and other systems with different solenoids, more on time can make the boost go down. So you need to understand what your solenoid is and how it is plumbed. So at the setup point here, we're going to use number 6, which means duty cycle control. Our aim is to find out what duty cycle makes what boost. Once we get that sorted, we can move to closed loop PID control. But today's webinar is about just getting the plumbing right and getting the ECU in control of the boost. So we're definitely sticking with duty control to start with. So the basic setup, if you go into functions, boost control, now into the aim boost table, in this table here, you will put the duty cycle numbers. Now, there's a few other tables that you need to get configured correctly. Now, to see what that information is, if you're in the boost control aim boost table, you can press F1 and you will get this help screen. And this help screen takes you through the other tables and parameters that you need to set. Basically, the proportional gain needs to be set to 1 and all other tables set to 0 and all other parameters set to 0 other than the max duty, which needs to go to 100. So if you get that part set up, then in the aim boost table down here, what duty you put here should be exactly what the solenoid will do. So if you go for a 20% duty cycle, that means the solenoid, depending on the polarity, will be on for 20% of the time and off for 80. Again, there is another parameter that will change that, so strike that next. Now, because there are different solenoids that, when plumbed in different ways, will change whether the boost goes up or down when they're on, we need to configure the polarity of the system. Now, this isn't easy to understand, unfortunately, but I'll try and cover it for you. So, as I said earlier, sometimes turning the solenoid on will make the boost go up, and sometimes, depending on the system, turning the solenoid on will make the boost go down. Now, if you want numbers in your boost aim table, to larger numbers to mean more boost and lower numbers to mean less boost, then you need to get the polarity setting here correct. So what this means is when we say 20%, does that mean 20% of off or 20% of on? I think is possibly the best way of looking at that. I've done a diagram to help understand that. So normal setup is bigger boost, aim duty numbers for more boost. So when we say we have a 20% duty and we go to 30 in the table, normally we'd expect that to make more. So again, as I said, different physical setups can mean duty up equals boost up, or duty up can equal boost down. So when we talk about duty, a solenoid is driven normally with 12 volts to one side, and the ECU grounds the solenoid. So we have battery supply going to the boost valve, and when the ECU takes the voltage to ground, then the valve turns on. So if we were to measure the voltage at this point, when the valve is off, there'd be 12 volts, and when the valve is on, there'd be 0 volts. So when the valve is on, we might say that's a 30% on for 30%. We would say this is a 30% duty cycle with the valve on for 30 and off for 70. Right, so if we have a polarity number of 0, that means the on time is the 30% refers to the on time. If we change the polarity number to 1, that means the 30% is referring to the off time. So for valves that make the boost go up when the valve is off, then the polarity is 1. Okay, so if you have a boost control system and you put in larger numbers as larger duty numbers in your boost aim table, and that makes the boost go down, fix that by changing the polarity in the setup. So now testing. First thing we need to do is go into the boost aim table. This is where we'll be entering numbers to get our boost to respond. Now there is a shortcut for that, and that's F7. So if you press F7, then you'll go straight to the aim boost table. Now normally you would expect an ideal situation is where we get a duty number of say less than 50, maybe down to 30, being your minimum boost, and a number of somewhere around 80 getting to be your maximum boost. So we're getting effectively somewhere between sort of 40 and 50% duty cycle spanning the boost control range that you want. And that gives the computer, when it comes to PID control, a nice amount of resolution to do what it needs to do to work well. So effectively, if you have the polarity configured correctly, you would start with a 0 duty and test how much boost the engine makes. Now if it makes your minimum boost setting, which is your spring setting, then everything's gone well. So if we have a spring of 20 pound, then I expect that should make 20 pound boost with a 0 duty cycle in the aim boost. Then you start progressively adding duty and testing a little bit at a time to see what duty cycle will make what boost. Now on the dyno, if everything's under control on the engine dyno, we might sit there and hold the engine at full throttle and quickly type in 20, 40, 60, 80% duty. Simply log the response. Now obviously we'll be watching for an overboost situation, and if we find that it overboosts at 20% duty cycle, potentially got an issue that we need to resolve. Now in most cases, if everything is plumbed correctly, you might find that, and especially if it's a factory system, nothing much will happen until it gets to about 30 or 40. And then between, as I say, 40 and 70 and 80, you'll get some boost change for a particular amount of duty change. Now, if you keep typing up and up and up and up and you get no boost increase, you need to come back and see why that is. Is the boost control system wired up correctly? Is there, not wired up, well, wired up to start with, but is there an issue with the plumbing of it? Is there a boost leak? Has the intercooler failed? There are many reasons as to why the engine doesn't make boost. Maybe the turbocharger is not correctly sized for the engine, and you're running it at high RPM, and you're doing this test, and it doesn't make any more than 20 pound, and you want to run 28. It could be that the turbocharger is not big enough to do the job. A way to find out if the boost control system is the fault is to jam the wastegate closed effectively. Now this is something that you must do with great care. What I mean by that, if I go back, go to a simple system. Effectively, in extreme cases, you can disconnect the hose from the boost control system here, and you could potentially wind on short, and sometimes the gates here have adjustments on them, and you can wind on or even wire the gate closed completely. So in other words, make sure that the boost control system, the wastegate itself, won't open, however you want to do that. So assuming you have the gate now physically jammed closed, and that there's nothing, no way the exhaust gas can be bypassed, very, very carefully bring the engine up to create a boost situation. Now, if it has big turbocharger and if your problem is actually something to do with the boost control, it will make a lot of boost, and so you will hit your overboost cut probably, or overboost the engine. You must be very careful doing that, and I'd suggest this isn't a good test to do with someone out in a car on a track. But nonetheless, you need to make sure that your physical turbocharger intercooler system has the physical capability of producing the boost that you want to run. If you don't, if the system can't produce the 28 pound, for example, that you want to run, then the computer will never get it to happen either. So assuming that the thing then makes 30 pound boost and hits the overboost cut, then we know at least that the reason it's not making boost is to do with the control system, and you can do the appropriate tests to work out why the boost doesn't go up. Now, it could be as simple as the hose blocked here. It could be the fact that the computer can't waste enough away to get the boost because the restrictor here is too big. There are many reasons, and you have to go through and try and diagnose what they are. Perhaps one of the other things you could also check is in the ECU setup, you can, in auxiliary output testing, test that the valve itself is pulsing. You can actually test that it pulses, change the duty during that test, and physically blow through the valve and make sure that it's passing air. If you've got it wired to the wrong auxiliary output, some part of the plumbing wrong, then for sure the boost won't go up or down. So that's effectively, that's the aim of the whole exercise. We want to see the desired boost reached by putting in a certain duty cycle in the table here. Now, while you're tuning this thing, you can actually drop the aim boost table down to just one number, just for the purposes of tuning. Simply push A for axis, go into the axis setup and untick both boxes, and you'll be down to one number, so a single number here for the aim boost. And this will allow you to easily just change the duty of the solenoid no matter what the RPM or throttle position is, and have control over the test. So you know you've got a good job done when you can type in a different number and get a different boost value. Once that's done, you're ready for the next stage, and that's setting up for PID control. Now, we'll cover PID control in a future webinar. That future webinar will be about setting up the normal position table, but it will assume that the computer has control over the boost. And for that to happen, we need to get this part sorted. So, got that, we're on for a successful boost control tuning session. Okay, so that concludes today's webinar, and other webinars can be viewed on our website. There are many different webinars there, and if you have any questions, our forum, place to ask them. There are many experienced people on the forums, not only our own staff but dealers and so forth quite often. So boost control is a difficult subject. There are many things that affect it, and your setup potentially could need special conditions. So jump on the forum, put the specifics of your setup there, and come to your aid as quickly as they can. Thanks for attending, and we'll see you next time.